Our entire galactic neighborhood is rushing toward a point we cannot see. The night sky looks calm, but astronomers have uncovered a profound and unsettling truth. A colossal, invisible force is pulling thousands of galaxies, including our own, on a journey toward an unknown destination. This is the mystery of the unseen gravitational giant. By the end, you will understand how this cosmic migration could reshape our most fundamental ideas about the universe. We will trace the evidence from strange galactic motions to voids that push and superclusters that pull. What does it mean for our place in the cosmos if we are all caught in a river of stars flowing toward a hidden source? In the 1970s, astronomers made a startling observation that challenged their understanding of the expanding universe. They confirmed that our Milky Way, along with our entire local group of galaxies, was not merely drifting apart in the cosmic expansion. Instead, it was racing in a very specific direction at a staggering speed of over 600 kilometers per second. This was not a random drift. Every galaxy in our vicinity was caught in the same current, moving together like leaves swept along by a powerful, hidden river. This coordinated motion was termed the bulk flow, and it was a profound anomaly. If the universe's expansion were perfectly smooth and uniform, as many models suggested, such a large-scale, directed flow should not exist. It was a clear signal that something immense was pulling us off course. To understand this, we need to grasp the idea of peculiar velocity. Think of the universe's expansion as the rising dough of a giant loaf of bread, with galaxies like raisins inside it. As the dough rises, all the raisins move apart from each other. That is the Hubble flow, the expected motion from cosmic expansion. But a peculiar velocity is an extra motion a galaxy has on top of that. It is the raisin also sliding sideways through the dough because of a local gravitational tug, perhaps from a nearby cluster of other raisins. What astronomers found was that our entire region of the cosmic loaf, thousands of galaxies wide, was not just expanding. It had a massive, shared, peculiar velocity, all sliding in the same direction. This meant the gravitational tug was not local. It was coming from something far larger and more distant than any known structure. Mapping these peculiar velocities became the first crucial step in a grand cosmic treasure hunt. By carefully measuring the redshift of galaxies, the stretching of their light, and subtracting the expected motion from universal expansion, scientists could chart the leftover flow. The map they began to draw was astonishing. It showed a vast river of galaxies, all streaming toward a single point in the sky near the constellations of Centaurus and Hydra. This was no small current. It was a cosmic migration on a scale that defied simple explanation. The sheer number of galaxies involved and the tremendous speed of their journey pointed to a source of gravity of almost unimaginable power. This initial anomaly set the stage for a decades-long quest. The hunt was on for the unseen giant capable of pulling thousands of galaxies, including our own, toward an unknown destination. The hunt for the source of this great galactic river led astronomers to a landmark discovery in the 1980s. By mapping the peculiar velocities of more and more galaxies, they triangulated the epicenter of the pull. It pointed toward a region of space near the border of the constellations Centaurus and Norma. There, hidden behind the dense plane of our own Milky Way's stars and dust, lay a gravitational behemoth they named the Great Attractor. Imagine a cosmic whirlpool, a vast, swirling eddy in the fabric of space. This was not a single object, but a dense knot of mass, a supercluster of thousands of galaxies bound together by their mutual gravity. The entire local group, including our Milky Way, was caught in its current, slowly spiraling inward toward this immense concentration of matter. For a time, it seemed the mystery was solved. We had found the mountain that was bending the river, but as measurements grew more precise, a troubling discrepancy emerged. The gravitational pull of the Great Attractor was powerful, but it was not powerful enough. The speed of our motion, the sheer momentum of the bulk flow, was greater than what the visible mass of the Great Attractor could produce. It was as if we had discovered a towering peak, only to realize its shadow stretched far beyond its base, hinting at a much larger, hidden mountain range still shrouded in fog. The Great Attractor was pulling us, yes, but something even more immense appeared to be pulling the Great Attractor itself. This meant our cosmic journey did not end there. The river of galaxies was flowing toward a point beyond this already colossal structure, toward a source of gravity so vast it could command the motion of superclusters. The search had to continue, pushing past the first giant to seek an even greater one hiding in the darkness. The discovery of the Great Attractor was just the beginning of a much larger story. In 2014, a team of astronomers made a breakthrough that fundamentally reshaped our cosmic address. Using sophisticated new maps of galactic motions, they identified a structure so immense it rendered previous maps of our neighborhood almost quaint. They named it Laniakea, a Hawaiian word meaning immense heaven. This is our home supercluster, a vast, web-like filament of galaxies spanning an almost incomprehensible 520 million light-years. Within this cosmic continent, containing over 100,000 large galaxies, the Great Attractor is not the final destination, but rather the gravitational center of the basin. Think of Laniakea not as a solid object, but as a river system on the grandest possible scale. The team mapped the peculiar velocities of thousands of galaxies, tracing how they flow through space under the influence of gravity. Just as water on Earth flows downhill into watersheds that drain into specific oceans, galaxies flow along gravitational gradients into specific basins. Laniakea is our basin. All the galaxies within it, including our Milky Way, are streaming along these invisible slopes toward the same dense core, the Great Attractor, like countless rivers converging on an inland sea. This redefined everything. Our motion was no longer just our local group being pulled toward a single point. It was our entire supercontinent of galaxies, a structure 100 times larger than our local group, engaged in a slow, stately drift. We had found the continent, and we understood its internal geography. Yet this monumental discovery also deepened the central mystery. If Laniakea itself is moving, what could possibly exert a gravitational pull on something of that scale? The force driving our bulk flow had to originate from beyond the borders of our immense heaven, from something that could tug on a supercluster as if it were a mere leaf. The search for the source was about to venture into even darker and emptier realms. The story of our motion took an even stranger turn at the very edge of the observable universe. In the early 2000s, astronomers studying the cosmic microwave background, the ancient afterglow of the Big Bang, noticed something that seemed impossible. They were analyzing the motion of massive galaxy clusters, some located billions of light years away, nearly at the limit of what we can see. The data revealed these incredibly distant clusters were not moving randomly. They appeared to be streaming in a uniform direction, a coordinated flow that aligned eerily with the motion of our own local universe. This phenomenon was dubbed the dark flow. The name itself hints at its profound mystery. It suggested these clusters were being tugged by something whose gravity should be far beyond our reach. According to our standard model of cosmology, nothing beyond the cosmic horizon, the limit of the observable universe, should be able to affect us. The universe's expansion should have severed any such connection long ago. Yet the data pointed to a vast, coherent motion on a scale that seemed to defy this fundamental rule. To grasp why this was so controversial, picture our observable universe as a sphere of light with a radius of about 46 billion light-years. We sit at the center not because we are special, but because this sphere represents the farthest distance light has had time to reach us since the beginning. Anything beyond that horizon is, by definition, unobservable. Its light has not had time to reach us, and its gravity, traveling at the speed of light, should not be able to influence us either. The dark flow hinted that something immense residing in that unobservable realm was exerting a pull. This pushed speculation into truly profound territory. Could the unseen giant pulling us be a structure of such staggering scale that it spans multiple cosmic horizons? Or could this flow be a remnant, a fossil imprint from the universe's first moments? Some theories suggest it might be a gravitational memory from the period before cosmic inflation, a time when regions now far beyond our sight were once causally connected. Others contemplate even more expansive ideas, like the gravitational tug of another universe in a vast multiverse, a neighboring bubble in the cosmic foam brushing against our own. While the dark flow remains a topic of intense debate within cosmology, its very proposal forces us to expand the search. It tells us that the source of our journey may not be a hidden supercluster within our universe, but something tied to the universe's very architecture. If the river of galaxies extends all the way to the horizon, then we must consider that its source lies in the deepest foundations of reality itself. But gravity is not just a force of attraction. To fully understand our motion, we must also consider the power of emptiness. In 2017, a team of cosmologists proposed a radical addition to the map of our journey. They suggested that our great galactic flow is not only caused by what lies ahead, pulling us forward, but also by what lies behind, pushing us from the rear. This idea centers on the discovery of the dipole repeller. The name itself is a clue. A dipole refers to two opposite poles, and a repeller is something that pushes away. This theoretical structure is not a supercluster of galaxies, but its exact opposite, a staggering cosmic void. It is believed to be located in the opposite direction of the Great Attractor, a region of space so profoundly empty it exerts its own strange form of gravitational influence. How can emptiness push? The key lies in understanding gravity on the largest scales. Einstein taught us that gravity is the curvature of spacetime by mass and energy. Where there is more mass, spacetime curves inward, creating a gravitational well that attracts objects. But the flip side is also true. Where there is significantly less mass than the cosmic average, spacetime is not as deeply curved. Think of the universe as a vast, undulating landscape. Superclusters are like deep valleys or mountain ranges where matter has pooled. Voids are like expansive, flat plateaus or even gentle hills. Now imagine placing a ball on this landscape. It will naturally roll downhill, away from the high, flat plateau and into the deeper valley. In this cosmic analogy, galaxies are like that ball. The relative lack of matter in a giant void like the dipole repeller means there is less gravitational pull holding things there. Meanwhile, the dense concentrations of matter in superclusters like the Great Attractor and beyond create a steeper downhill slope. So, galaxies do not experience a literal push from the void. Instead, they flow away from the underdense region because the gravitational pull from the surrounding overdensities is stronger. It is a cosmic imbalance, a gravitational deficit that acts like a shove. This dual model of a powerful pull from the front and a significant push from behind provided a more complete and elegant picture. It accounted for the full strength and direction of our peculiar velocity with greater precision. We were not just being reeled in by a hidden giant, we were also being gently nudged out of an immense cosmic emptiness. Yet, while this refined our understanding of the forces at play, it did not solve the ultimate mystery. The dipole repeller explains part of the why behind our motion's magnitude, but it does not identify the primary source of the pull. The core enigma remained and even grew sharper. If we are being pushed from an immense void and pulled toward an immense concentration of mass, what exactly is that concentration? What lies beyond the great attractor, with gravity so commanding it can define the flow of our entire supercluster? The map was becoming clearer, but the destination was still hidden in shadow. Deep in the direction of our flow, beyond the great attractor, lies a concentration of matter so vast it strains comprehension. This is the Shapley Supercluster, the single largest gathering of mass we have yet identified in our observable cosmic neighborhood. Located roughly 650 million light-years from Earth, Shapley is not merely a cluster of galaxies, it is a supercluster of clusters. Imagine a gravitational metropolis of staggering proportions, where dozens of rich galaxy clusters, each containing thousands of galaxies themselves, are all bound together in one immense structure. If our local supercluster, Laniakea, is a continent, then the Shapley Supercluster is an entire planetary hemisphere of mass. Its collective gravity creates a profound well in the fabric of spacetime, a slope so steep it influences the motion of galaxies across hundreds of millions of light-years. For many astronomers, Shapley is the prime suspect, the leading candidate for the unseen gravitational giant we have been tracking. It sits almost directly along the line of our bulk flow, a cosmic lighthouse whose beacon is pure gravity pulling everything toward it. The logic is compelling. We are flowing downhill, and Shapley represents one of the steepest and largest gravitational hills in our vicinity. Its immense pull is likely the dominant force shepherding not just our local group, but the entire Laniakea supercluster in its direction. Yet, as with every clue in this mystery, a complication arises. When scientists run the numbers, calculating the expected pull from Shapley's incredible mass and comparing it to the observed speed of our motion, a gap often remains. While Shapley is undoubtedly a titan, its gravitational influence, as we currently understand it, might not fully account for the tremendous velocity of the bulk flow. It is as if we have found a mountain range capable of bending rivers, but the rivers are flowing faster than the slope of that range alone should allow. This discrepancy suggests two intriguing possibilities. First, we may still be underestimating the true mass of the Shapley supercluster itself, perhaps due to vast reservoirs of dark matter intertwined with its visible galaxies. Second, and more profound, Shapley itself might not be the final destination. It could be, in turn, responding to a gravitational tug from something even more immense and more distant, a structure that lies behind it, hidden by its own brilliant glare. So the search narrows but does not end. We have identified a cosmic sovereign whose gravity shapes our journey, yet the full source of the current that carries us may still lie farther out in the deeper darkness. The map of our cosmic journey grew even more crowded with a startling discovery in 2016. Astronomers confirmed the existence of another gravitational titan, one that had been hiding in plain sight, or rather, hiding behind the blinding light and dust of our own galactic backyard. This is the Vela supercluster, a sprawling assembly of galaxies whose immense gravity adds a powerful new force to the equation pulling us through the cosmos. Its story is a testament to a fundamental challenge in mapping the universe, a challenge called the zone of avoidance. Our view of the cosmos is not a clean, open window in every direction. We live inside the disk of the Milky Way, a spiral galaxy filled with stars, gas, and immense clouds of fine, opaque dust. This dense band of material wraps around our entire sky like a celestial veil. For centuries, this zone of avoidance, as astronomers call it, blocked our view of anything lying directly behind it, creating a blind spot in our cosmic maps. It was like trying to map a distant mountain range while standing in a thick, permanent fog. The suspected location of the Vela supercluster sat squarely within this zone, its light absorbed and scattered long before it could reach our optical telescopes. To finally see it, scientists had to look with different eyes. They turned to radio astronomy and other techniques that can pierce the galactic fog. Radio waves, with their much longer wavelengths, can travel through the dust clouds that block visible light. By meticulously mapping the faint radio emissions from hydrogen gas in distant galaxies, and by using infrared surveys that sense the heat glow of stars through the dust, astronomers began to trace the outlines of hidden structures. The data revealed a colossal supercluster, a dense knot in the cosmic web rivaling the mass of the Great Attractor itself, sitting in the constellation Vela. The revelation of Vela was a game-changer for our understanding of the forces acting upon us. Its gravitational pull, now added to the combined might of the Great Attractor and the Shapley Supercluster, helps balance the cosmic ledger. The math of our peculiar velocity started to make more sense with this additional massive player included in the calculations. Yet, this discovery did not simplify the story. It deepened its complexity. We are not being pulled by a single, monolithic giant in the distance. Instead, we are caught in a vast cosmic tug-of-war, influenced by a complex web of superclusters. Each of these immense structures, Vela, the Great Attractor, Shapley, and likely others still hidden, contributes its own gravitational voice to the chorus directing our flow. Our journey is not a straight line toward a lone beacon, but a winding path down a gravitational landscape shaped by multiple mountain ranges. This paints a humbling and intricate picture of our place in the cosmos, where even our grand supercluster is just one piece in a larger, dynamic dance of matter and gravity. The oldest light in the universe holds a whisper of our present journey. This brings us to a third and profoundly fundamental clue written in the faint afterglow of creation itself, the cosmic microwave background. This is the relic radiation from a time when the universe was just 380,000 years old, a baby picture of the cosmos. For decades, we have known this ancient light is not perfectly uniform. It is dotted with tiny temperature fluctuations, mere millionths of a degree, called anisotropies. These are the cosmic equivalent of a fingerprint. Each slightly warmer or cooler patch corresponds to a region in the infant universe that was a tiny bit denser or emptier than average. Under the relentless pull of gravity over billions of years, those dense spots grew. They became the seeds for everything we see today, the vast cosmic web of galaxy clusters, superclusters, and the immense voids between them. The subtle patterns in this ancient light are the blueprints for the universe's large-scale structure. Now, here is where the mystery deepens. When scientists study these patterns with incredible precision, they find something peculiar. Some of the largest-scale anisotropies, the most significant warm and cool patches stretching across billions of light-years, show a curious alignment. Their orientation is not random. It points in a direction that echoes the very same direction of our local bulk flow, the great river of galaxies carrying us toward the unseen. This is a staggering connection. It suggests that the gravitational slope we are sliding down today, the pull from the Shapley supercluster and whatever lies beyond it, is not a local accident. Its origin may be traced back to the very first moments after the Big Bang. The seeds for today's titanic gravitational structures, the ones dictating the motion of our entire supercluster, were planted in the primordial fabric of the cosmos. Our local journey appears to be written into the universe's oldest memory. This clue ties the fate of our galactic neighborhood directly to the initial conditions of everything. It implies that from the very beginning the dice were loaded. The universe was born with a slight tilt, an asymmetry on the grandest scale, and we are still feeling its gravitational echo nearly 14 billion years later. It raises a profound question. Are we simply following a path laid down for us in the first fraction of a second of time? This invisible architecture is the key to the entire mystery. To truly grasp the power of the unseen giant, we must look beyond the glittering galaxies and into the dark foundation upon which they are built. The overwhelming majority of gravity shaping our cosmic journey comes from a substance we cannot see, touch, or directly detect: dark matter. Think of the universe's large-scale structure not as a collection of stars, but as a vast, intricate spiderweb spun across the void. This cosmic web is woven primarily from dark matter, a mysterious form of matter that does not emit, absorb, or reflect light. It interacts with the universe through one force only: gravity. And because there is so much of it, perhaps 5 times more dark matter than all the ordinary atoms in the cosmos, its gravity is the dominant sculptor. After the Big Bang, slight density fluctuations in this dark matter began to grow. Gravity acted like a cosmic amplifier, pulling more dark matter into the denser regions. Over billions of years, this process sculpted a magnificent filamentary structure, a network of immense, invisible threads stretching across the universe. Where these dark matter filaments intersected, they created dense knots, vast halos of invisible mass. It is within these halos that ordinary matter, the gas and dust we are made of, could pool, cool, and eventually ignite into stars and galaxies. The glittering galaxies we see are merely the visible tracers, the bright ornaments hanging on an unseen scaffold of dark matter. So when we talk about the gravitational pull of the Shapley Supercluster or the Great Attractor, we are not primarily talking about the pull of their brilliant galaxies. We are talking about the combined colossal gravity of their immense dark matter halos, the hidden mountain ranges of the cosmos. This reframes our entire quest. The mystery of the unseen gravitational giant pulling thousands of galaxies is at its heart a mystery of dark matter's distribution on the grandest scales. We are trying to map a mountain we cannot see by observing how the glitter on its slopes is sliding downward. Every measurement of peculiar velocity, every map of the bulk flow, is essentially a tool for charting the invisible topography of the dark matter landscape. It tells us where the gravitational wells are deepest, where the slopes are steepest. Pinpointing the ultimate source of our motion, therefore, means finding the most massive concentration of dark matter in our cosmic vicinity, the densest knot in the web. This is why the search continues, using the flow of galaxies as our guide to illuminate the dark. The universe is not a simple arrangement of isolated giants. To understand the full scale of the forces upon us, we must zoom out to a truly panoramic view. Scattered across the observable cosmos are structures so immense they redefine our sense of scale. Among them are the legendary Great Walls, like the Sloan Great Wall, and the even more colossal Hercules Corona Borealis Great Wall. Discovered through painstaking galaxy surveys, these are not solid barriers but vast, sheet-like filaments of the cosmic web, immense chains of superclusters strung together across billions of light-years. The Sloan Great Wall, for instance, is a filament roughly 1.4 billion light-years long, a staggering river of galaxies and dark matter. The Hercules Corona Borealis Great Wall may be even larger, perhaps 10 billion light-years across, a contender for the single largest structure we have ever identified. These are not destinations, but features of the landscape, continental divides in the gravitational topography of the universe. They represent the densest threads in the grand tapestry, where the dark matter web is thickest and its gravitational pull most profound. This brings us to the essential framework, the cosmic web. This is the fundamental architecture of the universe on the largest scales. Picture an enormous, three-dimensional spiderweb spun on a scale beyond human imagination. The bright knots where the web's threads intersect are our superclusters like Shapley or Laniakea. The long, dense threads connecting them are the great walls and filaments. And the vast, empty spaces between the threads are the cosmic voids like the dipole repeller. Everything is interconnected. gravity has woven ordinary matter and dark matter into this single, coherent structure over billions of years. Our Milky Way resides in a relatively small filament on the outskirts of the Laniakea supercluster, which is itself just one part of a larger wall that may connect to other immense structures. From this panoramic perspective, our mysterious motion begins to make a new kind of sense. We are not simply being reeled in by one hidden giant. We are responding to the combined gravitational melody of the entire cosmic symphony surrounding us. The Shapley Supercluster plays a powerful bass note pulling us forward. The Vela Supercluster and the Great Attractor add their own resonant tones from the side. The immense voids behind us contribute a profound silence that pushes us onward, and the gravitational slope of the larger filamentary walls we are embedded within sets the overall key. Our peculiar velocity, the Great Flow, is the net result of all these forces combined. It is the dominant chord that emerges when every gravitational influence in our corner of the cosmos is summed together. This shifts the entire quest. We are no longer hunting for a single monster in the dark. We are cartographers trying to map an entire invisible mountain range by feeling the pull on our ship. The unseen gravitational giant may not be a solitary peak, but the combined mass of several of the universe's grandest structures, all aligned in a way that their pulls reinforce each other in our direction. The mystery becomes one of precision mapping, of weighing the entire local universe to see if the sum of all its known parts, every wall, every supercluster, every void, can finally account for the relentless speed of our journey. If there is still a discrepancy after that ultimate calculation, then we will know for certain that something truly unimaginable still lies in the shadows, waiting to be found. This cosmic detective story now moves from telescopes to processors. To map the unseen giant, scientists have built entire universes inside supercomputers. These are not simple animations, but immensely complex digital laboratories governed by the precise equations of gravity, dark matter, and cosmic expansion. Projects like the Millennium Simulation and Illustris TNG are essentially time machines. They start with a digital representation of the infant universe, its conditions modeled on the subtle fluctuations we see in the cosmic microwave background. Then they set the clock forward. The simulation calculates, step by virtual step, how trillions of particles of dark matter and gas interact over billions of years, all under the relentless pull of gravity. What emerges from this digital primordial soup is breathtaking. Filaments of dark matter weave themselves into a vast cosmic web. Galaxies form at the intersections, clustering into groups and superclusters. Voids grow emptier as matter drains into the dense walls. These simulations don't just create pretty pictures, they generate predictions. They show us what the universe should look like, how structures should form, and how galaxies should flow if our theories about dark matter and gravity are correct. This is where the mystery of our motion meets the machine. Scientists run these simulations thousands of times, each with slightly different starting conditions or theoretical tweaks. Then they compare the results to our real, observed universe. They look for a simulated universe that produces a bulk flow matching our own, with galaxies streaming at the same speed and toward the same general region of the sky. When they find a close match, they can peer into the digital model's code. They can pinpoint exactly where, in that simulated cosmos, the greatest gravitational pull is coming from. They can trace the invisible slopes and valleys of dark matter that generated the flow. This process is a form of cosmic forensics. By finding the digital universe that best fits our reality, scientists can infer the likely mass and location of the real-world structures pulling us, even if those structures are still partially obscured from our view. It allows them to say, if our theories are right, then an attractor of a certain immense mass must exist in this specific direction, and it must be embedded within a larger filament of the web with a particular shape. These simulations are our most powerful tool for turning the subtle tug on our galaxy into a detailed map of the hidden architecture ahead. They transform the mystery from a question of what is pulling us into a precise investigation of how much and from where. The hunt for the unseen giant now employs a tool of astonishing subtlety. To measure the grand flow of galaxies, astronomers have learned to read the shadows they cast upon the oldest light in the universe. This technique is called the kinematic Sunyaev-Zeldovich effect, a name that hides a beautifully simple concept. It works like this. The cosmic microwave background, that ancient afterglow from the Big Bang, fills every corner of space. When a massive object like a galaxy cluster moves through this sea of primordial light, it leaves a faint but detectable imprint. Imagine walking through a gentle, steady mist. As you move forward, the mist directly ahead of you appears slightly warmer against your skin, while the mist behind you seems a tiny bit cooler. You are not changing the mist itself, but your motion creates a subtle temperature difference in the direction you are traveling. The kinematic Sunyaev-Zeldovich effect is the cosmic version of this. The hot gas within a galaxy cluster scatters the photons of the cosmic microwave background. Because the cluster itself is moving, it imparts a tiny Doppler shift to these photons. This creates an incredibly minute distortion in the temperature of the background radiation in that specific patch of sky. The signal is extraordinarily faint, a fluctuation of just a few millionths of a degree, but for modern telescopes it is a readable signature. It acts as a cosmic speed camera, recording not just that a cluster is moving, but precisely how fast and in which direction. Recent large-scale surveys have harnessed this effect with remarkable success. By combining data from telescopes like the Atacama Cosmology telescope and the Planck satellite, scientists have measured the collective motion of thousands of galaxy clusters. The results are a powerful, independent confirmation of the bulk flow. They do not rely on measuring galaxy redshifts and calculating peculiar velocities indirectly. Instead, they see the motion imprinted directly onto the fabric of the early universe itself. These measurements tell us the flow is real, it is coherent across vast distances, and its speed matches earlier estimates. The kinematic Sunyaev-Zeldovich effect turns the cosmic microwave background into a vast celestial canvas, and the moving clusters into brushes that leave streaks of evidence across it. By reading these streaks, we gain our most direct observational proof that immense, unseen forces are shepherding the architecture of our local universe. All this evidence points toward a profound and unsettling question. What if the sheer scale of this motion, the power of the unseen giant, is telling us something is wrong with our fundamental picture of the cosmos? This brings us to the heart of modern cosmology, and a potential crisis known as the lambda cold dark matter model tension. The lambda CDM model is our universe's operating manual. It is the beautifully successful standard theory that describes a cosmos dominated by dark energy, symbolized by the Greek letter lambda, and cold dark matter. This model rests on two cornerstone principles. The first is homogeneity, meaning that on the very largest scales, if you take a big enough chunk of the universe, it looks roughly the same everywhere, like a well-mixed batter. The second is isotropy, meaning the universe looks the same in every direction you look. These principles are why we do not believe we occupy a special place in the cosmos. They are the foundation upon which we interpret the cosmic microwave background, the expansion of space, and the growth of all structure. But the great bulk flow, if it is as vast and fast as some measurements suggest, pushes directly against these ideas. A flow that coherently moves thousands of galaxies across billions of light years implies a gravitational slope on a scale the standard model struggles to explain. It suggests an asymmetry, a lopsidedness in the distribution of matter that is simply too large to be easily accounted for within a universe that is supposed to be smooth on such immense scales. This creates a tension, a nagging discrepancy between prediction and observation, not unlike the famous Hubble constant tension concerning the universe's expansion rate. Is the unseen giant a sign that our cosmic rulebook needs a rewrite? The possibility opens doors to extraordinary ideas. Some physicists speculated could point to exotic, early universe phenomena, like primordial magnetic fields woven into the fabric of spacetime that helped steer the flow of matter. Others explore modifications to Einstein's theory of gravity itself, suggesting that on the largest scales, gravity might behave in subtly different ways than we have assumed. These are not fringe concepts, but serious investigations born from a desire to explain the data. Yet there is another, more conservative possibility. Could the Great Attractor complex simply be a rare statistical fluctuation? In a universe as vast as ours, even a model that predicts general smoothness might allow for the occasional colossal anomaly, a truly grand canyon in the cosmic landscape. Perhaps we just happen to live next to one of the largest gravitational valleys in the entire observable universe. Determining which answer is correct, whether we are witnessing a flaw in our foundations or a magnificent cosmic coincidence, is what elevates this mystery from a curious astronomical fact to a potential scientific revolution. The unseen giant is not just pulling galaxies, it is pulling at the very edges of our understanding. The answer to this cosmic riddle may soon be within our reach, thanks to a new generation of eyes on the sky. We stand on the brink of a golden age of cosmic cartography, where the unseen giant will finally be brought into focus. Leading this charge are three monumental missions, each designed to map the universe with a depth and breadth we have never before achieved. The European Space Agency's Euclid telescope, already in operation, is a dedicated dark universe detective. Its mission is to chart the geometry of the cosmos by measuring the shapes of over 1 billion galaxies across 10 billion light-years. It does this by observing a subtle effect called gravitational lensing, where the gravity of dark matter distorts the light from galaxies behind it. By meticulously measuring these tiny distortions, Euclid will trace the invisible scaffolding of dark matter itself, revealing the true gravitational landscape that shapes our flow. Following closely is NASA's Nancy Grace Roman Space Telescope, set to launch later this decade. Roman will conduct panoramic surveys of the sky with a field of view 100 times larger than the Hubble Space Telescopes. This incredible breadth allows it to perform a vast census of galaxies and measure their distances with immense precision. Roman will not only map where galaxies are, but also how they are moving through space in 3 dimensions. It will measure the peculiar velocities of millions of galaxies, creating a dynamic, flowing map of the cosmic web that will show us the gravitational currents in exquisite detail. On the ground, the Vera C. Rubin Observatory in Chile will soon begin the legacy survey of space and time, a 10-year project that will scan the entire southern sky every few nights. Its giant mirror and massive camera will detect billions of galaxies and track how their brightness changes over time. This relentless watch will allow scientists to measure the universe's expansion and the growth of structure with phenomenal statistical power, catching even the faintest whispers of gravitational influence across the void. Together, these missions represent a unified assault on the mystery. They will generate petabytes of data, creating a 3-dimensional atlas of the cosmos so detailed it will be like going from a hand-drawn sketch of a continent to a satellite image where you can see every tree. By combining their maps of dark matter distribution, galaxy positions, and peculiar velocities, scientists will be able to perform the ultimate cosmic accounting. They will weigh every supercluster, measure every void, and trace every filament in our local universe with unprecedented accuracy. For the first time, we will see if the sum of all known parts, Shapley, Vela, the great walls, the vast voids, truly adds up to the powerful pull we feel. If the math finally balances, the unseen giant will be revealed not as a single hidden monster, but as the collective might of the cosmic web's grandest structures. If a significant discrepancy remains, however, these telescopes will point us with unerring precision toward the location and mass of whatever truly lies in the darkness beyond our current maps. The river of galaxies is about to give up its source. Our journey through this river of stars forces a question far deeper than mere astronomy. It asks us to consider the ultimate fate of our galactic neighborhood and whether our motion implies a kind of cosmic destiny. Billions of years from now, will the Milky Way, Andromeda, and every galaxy in the Great Flow eventually converge, merging into a single, unfathomably massive supercluster? It is a staggering thought. This would not be a violent collision, but a slow, gravitational coalescence over timescales that dwarf human history, a final gathering in the universe's largest valley. This vision suggests we are in a state of endless falling, not toward a pit, but down an eternal slope within a gravitational landscape that is itself constantly changing. As dark energy pushes galaxies apart on the grandest scales, gravity continues its patient work locally, drawing communities together in an intricate, slow-motion dance. Our fate may be to become part of a future structure whose name we cannot yet conceive. This motion challenges one of the most cherished principles in cosmology, the Copernican principle. It is the idea that we do not occupy a special or central place in the universe. The cosmos is supposed to be homogeneous and isotropic, looking roughly the same everywhere and in every direction. Yet here we are, caught in a vast, coherent current moving toward one specific region of the sky. It feels intuitively as if we are flowing toward something special, as if that direction holds a unique significance. Does this mean we are, in fact, in a privileged location after all? Not necessarily. Think of it like this. If you stand in a river, the water flows in one definitive direction toward the sea. That does not mean your spot in the river is the center of the world, only that you are within a local current shaped by the broader landscape. Similarly, our bulk flow may simply mean we inhabit a particular slope in the cosmic terrain, a slope that exists precisely because the universe on very large scales is not perfectly smooth. There can be a dominant gravitational gradient in our vicinity without violating the idea that if you zoom out far enough, the cosmos has no true center and no preferred direction. The unseen giant, therefore, does not dethrone the Copernican principle but refines it. It teaches us that while we are not at the center of the universe, we are embedded within a specific, dynamic story written by gravity on the canvas of dark matter. Ultimately, this mystery transforms our sense of place. We are not passive residents of a static universe. We are participants in a grand, flowing architecture, passengers on a galactic vessel navigating currents set in motion billions of years ago. The pull we feel is a direct connection to the largest structures in existence, a reminder that our local group of galaxies is but a single leaf in a vast, drifting forest. To understand this pull is to read the signature of the cosmos itself, written in the language of gravity and motion. It humbles us, yes, but it also connects us to the grand narrative of everything. We are part of a journey whose destination is written into the oldest light and sculpted by the darkest matter, a journey that will continue long after our sun has faded. The river flows and we are carried within it, seeking always to understand the source of the current that guides our path. The most profound explanation for our motion may lie beyond the boundaries of our own reality. When all conventional sources within our universe seem insufficient to explain the great flow, science must look to the most radical possibilities. This leads us to a speculative but breathtaking frontier, the idea that the unseen gravitational giant is not of our cosmos at all, but a ghostly pull from a neighboring universe. In the framework of cosmic inflation and string theory, Our entire observable universe might be just one bubble in a vast, frothing multiverse, an endless cosmic foam where other bubble universes, with different physical laws and dimensions, constantly form and drift. Within this model, it is conceivable that another such bubble passed extraordinarily close to our own in the distant past, or perhaps even brushed against it. The gravitational influence of that other universe, an entire reality with its own immense mass and structure, could have tugged on the fabric of our space-time. This interaction, happening in the earliest moments of everything, could have set our entire local region of the cosmos into motion, imparting a coherent flow that has persisted for billions of years. The bulk flow we measure today, then, would be a fossil imprint of that primordial encounter, a permanent tilt in our gravitational landscape caused by a close call with another reality. While this idea remains firmly in the realm of theoretical physics and is far from proven, its power lies in the connection it forges. It links the very local mystery of why our galaxies are moving to the most profound questions we can ask about existence. It suggests that our journey toward the unknown is not just toward a hidden supercluster, but literally toward the lingering shadow of another cosmos. This transforms the search from a mapping exercise into a philosophical quest. If true, every measurement of the bulk flow becomes a way to sense the shape and proximity of something fundamentally alien and unreachable. It turns our telescopes into instruments that might, just might, be detecting the echo of a collision between worlds too vast to comprehend. The river of galaxies would then be more than a current. It would be a scar on our universe, a memory of a touch from outside. Yet this immense gravitational landscape is not the only force shaping our cosmic fate. There is a counterweight to the pull of the unseen giant, a repulsive force woven into the very fabric of empty space itself. This is dark energy, the mysterious driver of the universe's accelerating expansion. Our journey is caught in a fundamental cosmic tug of war, a battle between two invisible titans. On one side, gravity pulls matter together, building the great walls and superclusters that define the cosmic web. On the other, dark energy pushes space itself apart, acting as a kind of anti-gravity that stretches the distances between those structures over time. The bulk flow we are part of is a perfect snapshot of this ongoing conflict. On local scales within our supercluster and its immediate surroundings, the gravitational pull of the unseen giant dominates. Its immense concentration of dark matter creates a slope steep enough to draw thousands of galaxies together against the backdrop of universal expansion. We are flowing downhill in a valley whose walls are made of gravity. But if we zoom out to the grandest scales, the picture reverses. Dark energy appears to be uniform everywhere, and its repulsive effect grows stronger as the universe expands and becomes more empty. Over billions of years, this force will ultimately win the long war. The gravitational bonds that hold superclusters together will be overcome. The cosmic web itself will be stretched thin, and galaxies beyond our local group will be carried away by the accelerating expansion, receding until their light can never again reach us. This means our current journey has a paradoxical nature. We are rushing toward a gravitational center, even as the space between that center and everything else is being steadily inflated by dark energy. It is like trying to walk up an escalator that is moving downward. The local effort is real, but the larger system is working against you. Understanding the precise mass and location of the unseen giant is not just about solving a local mystery. It is about calibrating this cosmic competition. By measuring the strength of the gravitational pull in our vicinity with extreme accuracy, we can better understand the opposing push of dark energy. It helps us refine our models of how structure forms and evolves within an expanding universe. This data allows us to run more precise simulations to predict the future large-scale structure of the cosmos. Will the Great Attractor complex hold together for 100 billion years, or will dark energy tear it apart sooner? The fate of our galactic neighborhood and the ultimate shape of the cosmic web depends on the balance of these two unseen forces. Our motion is a single data point in that grand calculation, a fleeting glimpse of the universe in transition, caught between the urge to coalesce and the imperative to fly apart. This shift in understanding mirrors a profound pattern in human history. Centuries ago, the prevailing view placed our planet at the absolute center of creation. The sun, the moon, the stars, all were believed to revolve around a stationary Earth. This geocentric model felt intuitively true. It was what our eyes told us every single day. The idea that we were, in fact, orbiting the sun seemed not just incorrect but almost heretical, a demotion from a place of cosmic privilege. Yet, when that intellectual revolution finally took hold, it did not diminish our world. It expanded our universe. It revealed a solar system, a grander stage on which our planet played a part. We traded a comforting illusion for a magnificent, humbling truth. Today, we are living through a similar revolution, but on a scale that makes the solar system seem like our own backyard. For a long time, we understood our place as orbiting a star within a galaxy, and our galaxy as part of a slowly dancing local group. That was our modern cosmic address, but the discovery of the great bulk flow shatters that static picture. We are not merely orbiting, we are voyaging. Our entire local universe, a region encompassing hundreds of millions of light years and thousands of galaxies, is in transit. This is a move from geocentrism to what we might call cosmocentrism, the realization that even our grandest cosmic structures are not fixed points, but passengers on a larger journey. The unseen gravitational giant is the new sun we did not know we were falling toward. This represents another staggering step in our journey of cosmic humility. First, we learned we were not the center of the solar system. Then, we learned our sun was not the center of the galaxy. Now, we are learning that our galaxy, and even our supercluster, is not an isolated island, but a ship caught in a current flowing through the dark matter sea. Each revelation displaces us from a presumed center, only to embed us within a vaster, more dynamic, and more interconnected story. It tells us that the forces shaping existence operate on scales we are only beginning to map, and that our perception is always limited by our local vantage point. The true architecture of the cosmos reveals itself not in what is brightly visible, but in the silent, persistent pull of gravity on everything we can see. This grand quest to map the unseen is not reserved for professional astronomers alone. In a beautiful twist, some of the most important eyes on the sky belong not to giant telescopes, but to people just like you, sitting at home with a computer. This is the world of citizen science, a global movement where public curiosity directly fuels discovery. For nearly 2 decades, projects like Galaxies have harnessed the incredible pattern recognition of the human brain to accomplish tasks that even sophisticated algorithms struggle with. Volunteers from around the world log on to look at images of distant galaxies captured by robotic surveys. With a simple click, they help classify a galaxy's shape. Is it a majestic spiral, a smooth elliptical, or a distorted merger? This human-powered sorting has been phenomenally successful, leading to the discovery of entirely new classes of objects and helping to map the large-scale structure of the universe. Each classification is a small but vital data point, a single star added to a growing chart of the cosmic web. It is a powerful reminder that the tools for cosmic exploration are becoming more democratic. You do not need a PhD to contribute to our understanding of the gravitational giant. You just need curiosity and an internet connection. This collaborative spirit transforms the mystery from a distant abstraction into a shared human endeavor. When you help classify a galaxy, you are not just looking at a pretty picture, you are actively tracing the threads of dark matter, adding your observation to the collective effort to weigh the unseen structures that pull us. It makes you a part of the story, a modern-day cartographer helping to fill in the blank spaces on our map of the cosmos. And this public partnership is about to enter a new era of unprecedented scale. The Vera C. Rubin Observatory's legacy survey of space and time will soon begin, generating a torrent of data so vast it will image the entire southern sky every few nights for a decade. It will catalog billions of galaxies, stars, and solar system objects, creating a cinematic view of a dynamic universe. This deluge of information will be far too much for any small team of scientists to process alone. The need for public eyes and minds will be greater than ever. New citizen science platforms will emerge, inviting people to spot gravitational lenses, track asteroid movements, and flag unusual galaxies that could be markers of hidden mass. Every anomaly spotted by a volunteer could be the clue that points toward a previously unknown supercluster or a vast void, refining our model of the gravitational landscape. This is the true power of the endeavor. It demonstrates that big science is a profoundly human collaboration. It connects a retired teacher in Melbourne, a student in Mumbai, and a programmer in Montreal to the same fundamental question that has driven our species for millennia: what is our place in the cosmos? By participating, you become more than a spectator. You become a contributor to one of the greatest detective stories ever told, helping to pinpoint the source of the river that carries us all. This profound pull of the unseen has always resonated beyond the observatory. The silent, invisible force guiding thousands of galaxies is not just a scientific puzzle, it is a wellspring of profound creative inspiration. For artists, musicians, and writers, the Great Flow offers a powerful metaphor for fate, connection, and the hidden currents that shape existence. Their work humanizes the science, translating cold data into emotional experience and reminding us that the quest to understand the cosmos engages the full spectrum of the human spirit. Visual artists, for instance, grapple with depicting the invisible. Some create stunning digital renderings that transform velocity maps into rivers of light, with galaxies like brilliant droplets streaming along luminous filaments toward a dark central mass. These are not literal illustrations, but emotional interpretations of the data, giving form to the gravitational landscape we can only infer. Others work in physical media, using layers of paint, glass, or sculpted material to represent the depth and flow of cosmic structure, making the intangible feel almost tactile. In the realm of sound, composers have undertaken a fascinating process called data sonification. They take the actual velocity measurements of galaxies, the precise numbers detailing their speed and direction, and assign musical notes or tones to them. A galaxy moving slowly might be a low, sustained cello note, while one racing faster becomes a higher pitch on a violin. When played in sequence according to their position in the sky, the data becomes a haunting, ethereal symphony. What you hear is not a melody written by a person, but the literal sound of our galactic neighborhood in motion, a choir of stars singing the song of their journey toward the unknown. This auditory translation reveals patterns and harmonies within the numbers that might be missed by the eye alone, offering a completely new way to perceive the cosmic flow. Writers and poets, too, are drawn to the metaphor. The Great Attractor complex appears in science fiction as a mysterious destination, a cosmic siren call pulling civilizations on a pilgrimage whose purpose is unclear. In poetry, it becomes a symbol of all the unseen forces that guide our lives, the silent tides of history, love, or chance that pull us along paths we do not fully comprehend. This creative response is not a diversion from the science, it is a vital part of the conversation. It fulfills a deep human need to connect emotionally with the vastness revealed by our instruments. The equations describe the how, but art explores the why of our wonder. It takes the cerebral concept of a bulk flow and asks what it feels like to be a part of it. This fusion of rational inquiry and imaginative expression shows that facing the cosmic unknown does not require us to choose between logic and awe. Instead, they are two currents in the same river, both essential to navigating the profound mystery of where we are going and what it means to be carried within this immense flowing dark. The human story behind the data is just as compelling as the cosmic mystery itself. To truly appreciate this search, I want to share a perspective from someone at the forefront, a cosmologist whose daily work involves chasing this invisible giant. In a hypothetical conversation, they might describe the moment the puzzle truly clicked. It was not a single dramatic event, but a slow, dawning realization while staring at a map of peculiar velocities. The numbers were not adding up. The galaxies were moving with a coherence and speed that the standard models simply could not accommodate. That initial anomaly, they would say, was equal parts thrilling and deeply unsettling. It was the feeling of standing at the edge of a cliff, knowing the landscape you had memorized was about to change forever. The daily reality of this work, they explain, is a constant dance between frustration and wonder. A significant part of the job involves working with incomplete maps, piecing together the cosmic jigsaw puzzle when half the pieces are hidden behind the zone of avoidance. It is an exercise in patience, building statistical models and running countless simulations to infer what must be there, based on the subtle gravitational tugs we can measure. They describe the collaborative nature as absolutely essential. Modern cosmology is not a solitary pursuit. It is an international conversation happening across continents, with teams sharing data from telescopes in Chile, satellites in space, and supercomputers in Europe and America. A breakthrough in understanding the flow might come from a graduate student's code in Tokyo being combined with a radio survey analyzed in Cape Town. The most profound part, our cosmologist reflects, is the quiet understanding that they are not just charting empty space, they are mapping the history and future of our corner of existence. There is a tangible thrill in knowing that the next data release from a new observatory could be the one that finally balances the equation or, more excitingly, deepens the discrepancy in a way that forces a fundamental rethink. That is the ultimate goal, not merely to find the missing mass, but to understand if our universe's operating manual needs a new chapter. The possibility of contributing to a textbook rewrite, of helping to refine humanity's most fundamental story of where we come from and where we are going, is what makes the long hours and complex math feel like a profound privilege. This quest, grounded in human curiosity and perseverance, reminds us that the river of galaxies is not just a physical phenomenon. It is a narrative we are all helping to decode, one observation at a time. The allure of a single, monstrous object pulling us in is a powerful one. It is easy for the mind to leap toward a familiar science fiction image, a supermassive black hole of impossible scale, or a hidden, wandering rogue planet, a cosmic planet X on a galactic scale. These are compelling stories, but they are not the reality of the unseen giant. The truth is both more diffuse and, in its own way, far more magnificent. What we are tracking is not a singular, dense point of destruction. It is a sprawling continent of mass, a vast region of space where the cosmic web is drawn into an exceptionally dense knot. This gravitational anomaly is not a black hole's intense, localized grip, but the collective, gentle slope created by thousands of galaxies and the immense, invisible halos of dark matter that surround them. Think of the difference between being sucked into a whirlpool and floating down a wide, slow river toward an inland sea. One is a violent, singular event. The other is a stately migration shaped by the entire landscape. A black hole, even a supermassive one at a galaxy's heart, has a gravitational influence that weakens significantly with distance. Its power is fierce but local. To move entire superclusters, you need gravity's pull to be felt across hundreds of millions of light years, and that requires an immense amount of mass spread across a vast volume. That is exactly what a supercluster complex provides, a gravitational well so wide and so deep that galaxies flow into it over cosmic epochs. The reality dismantles the need for a fictional villain. A lone dark star or a hidden planet, no matter how massive, simply lacks the sheer scale to orchestrate the motion we observe. The genuine mystery lies in the architecture of darkness itself, in mapping how these diffuse clouds of dark matter have clumped together to form the largest structures in existence. This shifts our wonder from a singular monster in the dark to the grand design of the cosmos. The awe is not in a fictionalized point of no return, but in the realization that we are navigating a universe textured by invisible mountains and valleys, a landscape whose sheer size and subtle slopes dictate the journey of every star within it. But why does this search for an invisible mountain in the dark matter web matter to us here and now? In a world facing immediate challenges, the pursuit of a mystery billions of light years away might seem like a luxury. Yet this very quest embodies something essential to our humanity, a cosmic curiosity that has practical, inspirational, and profound value. First, it is an unparalleled engine for innovation. The need to see the unseen, to measure the immeasurable, pushes our technology to its absolute limits. Every new telescope, like Euclid, Roman, and the Vera Rubin Observatory, is a masterpiece of engineering born from this desire. The algorithms that process their data, the supercomputers that run the simulations, even the fiber optic networks that shuttle that information around the globe, all represent leaps forward in computing and communication. The tools we invent to map the dark universe inevitably find uses closer to home, in medicine, data science, and materials engineering. The search itself builds better machines and sharper minds. Beyond the technology, it ignites a spark of wonder. The image of a river of galaxies flowing toward the unknown is a powerful story. It captures the imagination of a student gazing at the night sky, planting a seed that might grow into a career in science, engineering, or mathematics. It reminds us that the universe is a place of magnificent, unsolved puzzles, inviting the next generation to become the problem solvers and explorers of tomorrow. This mystery is not just about astrophysics, it is about nurturing the innate human drive to explore and understand. On the deepest level, this pursuit answers a fundamental need for context. For millennia, we have looked up and asked where we are and what it all means. The discovery that we are part of a great cosmic migration provides a new chapter in that ancient story. It situates our tiny planet within a dynamic, flowing architecture of staggering scale. This perspective can be humbling, but it is also unifying. It underscores that we share a single, fragile spacecraft, Earth, as it journeys through this grand gravitational current. In an age of division, contemplating a shared destiny shaped by forces beyond any human control can foster a sense of global citizenship and a longer view of our collective future. The value of seeking the unseen giant, therefore, is measured not in economic output, but in the expansion of human knowledge, the inspiration of young minds, and the cultivation of a cosmic perspective that reminds us of our common voyage in an immense and mysterious universe. So where does the evidence ultimately lead us? The current scientific consensus paints a picture not of a lone monster, but of a cosmic confluence. Our great journey is likely the result of a multi-source gravitational model, a grand sum of forces from across our local universe. The primary pull appears to come from the combined might of immense superclusters, chiefly the Shapley Supercluster acting as the dominant anchor ahead, with significant contributions from the Great Attractor and the more recently mapped Vela Supercluster from the side. These are not isolated peaks, but interconnected mountain ranges in the dark matter web their gravitational slopes aligning to create a powerful current in our direction. At the same time, we cannot ignore the push from behind. The immense dipole-repeller void, with its profound lack of mass, creates a relative gravitational deficit. We flow away from this cosmic emptiness because the pull from the dense concentrations ahead is simply stronger. It is a perfect example of cosmic imbalance in action. This dual explanation of multiple attractors pulling and a major void effectively pushing accounts for the bulk of our observed motion with remarkable elegance. It suggests the unseen gravitational giant is not a single entity waiting to be discovered. Instead, it is a complex gradient, a vast slope in the fabric of spacetime sculpted by the entire architecture of the cosmic web in our vicinity. We are flowing down the gravitational equivalent of a continental watershed, where every hill and valley contributes to the direction of the river. Yet, even this sophisticated model may not be the final word. The full picture is not yet complete. There could still be significant hidden mass lurking within the zone of avoidance, regions still obscured by our own galaxy's dust. Our maps, while improving daily, remain works in progress. It is also possible that even larger structures exist just beyond the current limits of our most ambitious surveys, their gravitational whispers only now beginning to be felt in our data. The search continues not for a singular beast, but for a more precise census of the entire cosmic neighborhood. Every new telescope survey adds another piece to this immense gravitational puzzle, helping us weigh the known universe to see if the scales finally balance. For now, the best guess is a humbling and magnificent one. We are moved by the collective voice of the cosmos around us, a chorus of gravity from structures both seen and unseen, all singing the same slow, stately song that carries us into the dark. The next chapter of this cosmic story is already being written, and you can watch it unfold. The coming years will bring a cascade of data that could reshape our map of the unseen. The first major milestones will be the initial data releases from the Euclid and Nancy Grace Roman space telescopes. These won't be simple press release images, but vast public archives of measurements. Scientists around the world will dive into these numbers, generating new, ultra-precise maps of dark matter distribution and the peculiar velocities of millions of galaxies. Look for headlines about the first three-dimensional flow maps derived from this data, charts that show the river of galaxies in finer detail than ever before. Alongside this, increasingly sensitive measurements of the kinematic Sunyaev-Zeldovich effect will provide an independent, powerful check on those flows, confirming their speed and direction with even greater confidence. A pivotal moment could be the identification of a new, dominant supercluster, a structure previously hidden behind the zone of avoidance or simply too diffuse to see, whose gravity finally balances the cosmic equation. This is not passive science, it is a dynamic, collaborative detective story happening in real time. To follow along, consider tuning into the public channels of the major observatories and collaborations, like the European Space Agency for Euclid updates, NASA for Roman news, and the Vera C. Rubin Observatory. Reputable popular science journals and websites offer excellent translations of these complex findings into accessible stories. The mystery of the Great Attractor Complex is no longer a static puzzle in a textbook, it is a living investigation. The next few years promise a revolutionary leap in our understanding, potentially revealing not just where we are flowing, but fundamentally why the cosmos around us is shaped the way it is. We are all witnesses to a new era of cosmic cartography, where the final contours of the unseen giant will slowly, surely come into view. The river of galaxies carries us forward, but the true destination of this journey has always been a deeper understanding. Our search for the unseen gravitational giant has charted more than a map of dark matter. It has traced the contours of human curiosity itself. From the first perplexing measurements of galactic drift to the panoramic visions of supercomputer simulations, every clue has pulled us further from a static universe and into a cosmos alive with motion and connection. This mystery has not merely been about locating a hidden mass, it has been a relentless test of our most fundamental theories, pushing the lambda cold dark matter model to its limits and inviting whispers of ideas as profound as a multiverse. It has driven the creation of magnificent tools, from space telescopes that are time machines to citizen science platforms that turn global curiosity into data. Most importantly, it has performed a quiet revolution in perspective, reminding us that we are not placid residents of an island universe, but travelers on a grand scale, participants in a narrative written by gravity across billions of years. We may not yet have a complete portrait of the giant, but the pursuit has already given us a gift, a universe far more dynamic, woven together, and wondrous than the static starscape of our ancestors. So when you next look up at the night sky, see it not as a fixed tapestry, but as a flowing current. Each point of light is a galaxy, and each galaxy is a vessel in that immense, silent river, all moving together toward a horizon we are only beginning to chart. The unknown still calls from the darkness, not as a void, but as an invitation. As we continue to look deeper with ever sharper eyes, we discover that the greatest reward is not always a final answer. Often, it is the revelation of a grander, more beautiful question waiting just beyond the light. If this exploration of cosmic mysteries has captivated you, there are countless more journeys to the edge of understanding waiting to be shared. Let us know in the comments below what you believe the ultimate nature of this unseen giant might be.